It's my distinct pleasure to introduce Dr. Amy Mainzer. She's here. I think, is this the first time you've been to the CFA? It's amazing. This is the first time she's visited here. Amy finished her PhD from UCLA in 2003, and she's done, even before that, but since, some very remarkable work involving both Spitzer and WISE. She is the PI of NEOWISE, which is this extension to WISE that has done really fantastic work discovering minor planets in our solar system, unveiling not only size distributions but albedo distributions. And I think you'll be quite excited to hear some of the results that they've gotten. This is really a very effective team that she's assembled. She's also a PI of NEOCAM. I hope you'll hear a little bit about that. But I'm not going to take any more of Amy's time because she's going to show some very fantastic work. So please, Amy.
Oops. If I don't strangle myself with the cord here. Thanks, Matt. Can everybody hear me okay? Great. Okay, thanks so very much. It's really great to be here and to see a lot of really familiar faces from the past and from other projects. So I'm here to talk a little bit about the small bodies in our solar system, the asteroids and the comets, and just what we know about them and what we would like to know, and how some recent new mission data has filled in our understanding of these populations. Now, for a lot of you, this is going to be completely old hat, and I apologize, but since there are a lot of people who don't necessarily think about the solar system bodies all that much, I always like to start off with just a very brief guide to the solar system. Most of the asteroids in our solar system live in the main belt between Mars and Jupiter, and they're an ancient population. They've been there for billions of years, and in most cases, that's where they stay. They just don't really go anywhere, and they've been very stable over long periods of time. They've been heavily processed through collisions with other asteroids and through non-gravitational forces that sort of move them around a little bit. But generally, they stay there for long periods of time, and as of today, we know of roughly 600,000 of these objects. Now, by contrast, the near-Earth objects refer to the asteroids and comets that enter the region around the Earth's orbit. And unlike the main belt asteroids, which are quite ancient, the NEOs, as they're called, are extremely young. They tend to last for only a few millions to a few tens of millions of years. Once they reach the region near Earth, basically one of three things happen. Eventually, they either hit the sun, they get scattered completely out of the region, and in some cases even just go way out into the outer reaches of the solar system, or eventually they hit a planet. So the question is, how often do they hit the Earth? That's one of the first questions. And you'll notice also, too, that there are clusters of asteroids here, these green blobs. These are the Jovian Trojans. These are in gravitational resonance with Jupiter. Now, back to the NEOs. So unlike the main belt asteroids, where we know of hundreds of thousands, the NEOs, we only know of about 11,600 today, roughly. And that number is growing by about 1,000 per year on average. Okay, so this last year, 2013, was really a remarkable year for asteroid scientists. And I'm going to just use my laptop audio here. Just bear with me. But this was really a strange day because we knew that there was going to be an asteroid making a very close pass by the Earth, but it was well known that it would not hit. And so I was actually driving home from LAX and listening at about 11 o'clock at night and listening to the radio. And that's what happened. And I thought, wait a minute, this is nuts. This asteroid is not supposed to hit the Earth. We know where it's going. What is going on here? This is really, really bizarre. And all of these subsequent booms that you're hearing are the fragments bursting apart. So the object left this huge contrail in the sky. And it became clear that it was an extremely high altitude airburst. Because of the time delay from the appearance of the contrail to the sound waves arriving on the Earth. About 95% of the energy was actually dissipated harmlessly in the upper atmosphere, tens of kilometers up. So most of it didn't actually reach the ground, but what did reach the ground caused a fair amount of chaos, mostly in the form of broken glass. And most of the injuries were glass flying. People, when they saw the contrails, they ran to the window, and because it took, yeah. And then these guys, now they did get out. There's a door. They do go out the door. he makes it out the door, which is good, but then there's these other guys who are still under there, you know. And then, so that doesn't go so well. But anyway, they eventually get out of the thing. So, but you know, anyway, most of the injuries were because people ran to the windows when they saw the contrail. It took about a minute or 2 minutes for the shock wave to reach the Earth. And of course, people who remembered the duck and cover days knew not to go to the window, but rather to stay under the desks. And thus they avoided some of the flying glass injuries. But a lot of people ran right for the windows, and that's what caused most of the injuries. So, but nobody died, fortunately, and it was a very tiny asteroid. This turned out to be roughly 17 to 20 meters across, as estimated from various methods, but including infrasound stations that are essentially listening for nuclear weapons violations or something like that, or missiles. And it basically had about 500 kilotons of TNT, but most of that energy dissipated harmlessly in the upper atmosphere. So in the end, this is actually a piece of it right here. This is my very own little piece of the rock. I managed to get a small piece of this, and it's a really interesting rock. As far as meteorites go, this is one of the most common types of meteorites. It's an ordinary chondrite. And what is kind of noticeable about it, though, is you can see these veins, these dark veins running through it. And these are records of previous collisions that the object has undergone tens of millions of years ago. So it's a heavily processed object. You can see it's got a nice fusion crust on it from the entry into the Earth's atmosphere. But basically, this is a fragment of an asteroid that was long ago impacted by other asteroids, probably many times over the course of its long history. And eventually, it got in the way of the Earth. Now, why was it not noticed beforehand? Well, it came out out of the direction of the sun. In the very last minutes before its final approach, it basically came out from about, I think it was around 10 degrees or so away from the direction of the sun. So, during the daytime sky, where ground-based observers can't see. And it was a very tiny object. So it was extremely dim and faint for, basically the minute that it got even a little bit away from the Earth, it would have been far too faint to be observed. So this begs the question, of course, how often does this sort of event happen? And we have some very rough estimates, but we'd like to refine them. And this is what we've been working on in my group. But basically, we know that really large mega events happen about every 100 million years. There's a little bit of the anthropic principle here. I mean, we wouldn't be here if these sorts of giant collisions happen more frequently. So we know that they're very rare. The estimate is sort of a 1 kilometer impactor about every 500,000 years or so. And down at the time scale or the size scale of 20 to 30 meter objects, it's about every few hundred years, perhaps, give or take. But again, small number statistics make this somewhat difficult to constrain. And of course, this is the famous meteor crater in Arizona, which was created by an object not that much larger than the Chelyabinsk impactor. That was about 50 meters. But the difference is rather than an ordinary stony meteorite, this was thought to have been caused by an iron. So considerably higher density and therefore a much bigger impact. It wouldn't have just broken glass. Okay, so of course this is the big one, the Chicxulub impactor, which was a very massive thing. It was about 5 to 10 kilometers across. And it was the equivalent of 10 times the world's nuclear arsenal all dropped in one place. Essentially, it created a huge, massive amount of damage. And the ring-shaped structure here is visible underneath the Gulf of Mexico. And what it really did was it basically wiped out about 70% of all land animals and about 50% of all marine species. You can see here, this is a plot of genera, so one rank up from species, as a function of time. And life is more or less lumping along here, becoming more and more and more diverse. And here's the event. This is marine life. So things under the water were more protected than the terrestrial animals. In any case, it was large. Okay. So, but again, I think astronomers as a whole kind of thought, well, these are events of the distant past, and they really don't happen in the present day. And this was one of the events that really changed people's minds. In 1994, a comet was discovered on a collision course with Jupiter, and Jupiter, of course, shredded it into lots of pieces. The question was whether or not Jupiter would even notice the impact of this comet, because Jupiter is so massive. And of course, subsequent imaging revealed that, yeah, it actually did notice, and it left these pretty large scars. And of course, each one of these is about the size of the Earth. So that really got people's attention, and I think it's safe to say that helped to give rise to the idea that maybe we should actually begin surveying for near-Earth objects in a more systematic way. So this is a plot that basically shows the discovery of near-Earth asteroids as a function of time. The red objects are the class that are generally thought to be a kilometer and larger, so the really large planet buster type asteroids. And you can see here in 1994 is where things really started to pick up. But it's important to note that most of the surveys that do the lion's share of the work here are really done by very modest-sized telescopes. They're sort of 1 to 2 meter class observatories. They're not really very big observatories by any stretch. So while the 1 kilometer objects appear to be flattening out, these smaller objects just keep going up and up and up, indicating that we haven't run out of objects anytime soon. So one of the questions with the 1 kilometer objects that people wondered about is, have we really found all of the population or almost all of the population, or is there some category of large asteroids that we're systematically missing? So this is one of the things that people have wanted to look at. So keep that in mind for later. Okay, so this is our current suite of telescopes that do most of the work these days. Now, linear is really no longer active, but the Catalina Sky Survey and the Pan-STARRS telescopes in Arizona and Hawaii find almost all of the near-Earth objects that we see today. And like I said, they're discovering new objects at a rate of roughly 1,000 per year. And now, of course, we also have our first infrared survey, NEOWISE, which I'll talk about in a bit. So, and that time is now. Okay, so WISE is the Wide Field Infrared Survey Explorer mission. And this is a medium-class NASA Explorer. So it's a fairly small-sized project for a NASA mission. It's about $320 million. It's a 40-centimeter telescope that was designed to survey the entire sky at 4 wavelengths, imaged simultaneously, between about 3 and 20 microns. And we had to use a 2-stage solid hydrogen cryostat to cool the longest wavelength channels. So I won't repeat too much of the seminar from lunch today, but basically the class of detectors we are stuck with using at the 12 and 22 micron channels has to be cooled to around 8 Kelvin. And that really necessitated the use of the solid hydrogen. So it launched in late 2009. Ned Wright from UCLA is the principal investigator of WISE. And the mission surveyed the whole sky, finally ceasing operations in February of 2011. And the primary purpose for the mission had nothing to do with asteroids. It really was designed to carry out an all-sky map at infrared wavelengths for really general purpose astronomy, and also with a couple specific science goals in mind, finding ultra-cool brown dwarfs, as well as ultraluminous infrared galaxies. And the asteroids were kind of an afterthought, but it turns out that it was actually pretty good at seeing asteroids. And that had a lot to do with the combination of the wavelength, the cadence, and the field of regard. So the WISE mission is in a sun-synchronous polar orbit. So it's basically about 525 kilometers. And it always observes near 90 degrees solar elongation. So this is a region of sky that's sort of the twilight and dawn sky on Earth. It's reasonably difficult for ground-based telescopes to spend a lot of time there just because of the diurnal cycle. But this is where we observe all the time. So the scan coverage results in lots and lots of coverages up at the ecliptic poles, and on average about 12 observations in the ecliptic plane. So for asteroids, this actually turns out to be pretty good. And what we do is we use a very small mirror to quickly flip back and forth between exposures. The mirror is only about yay big, maybe the size of a compact. And that is what allows us to switch very quickly between the different fields. Okay, so here's a picture of the observatory just before launch. And you can see here it's not really that big. This is perhaps about half of life size. It's about 15 feet tall. And it's got the solid hydrogen cryostat up there, the star trackers with the red caps, solar panels, all the usual stuff that a spacecraft has. But what about the asteroids? Well, it turns out, of course, this was not a mission that was dedicated to searching for asteroids. And the original plan was to take all of the exposures, and like I said, there were on average about 12 exposures on the ecliptic plane, rising to hundreds at the poles. The original plan was to co-add all of those exposures together and then just serve the image atlas and catalogs that resulted just from the co-adds. And that's great if the targets that you're looking for don't move or change on timescales of hours. But it's really bad for asteroids because the co-adding just washes them right out. So we were actually given some extra resources from the Planetary Science Division of NASA to do a couple of things. First, to archive all of the individual exposures as well as the extracted sources for each individual image. And then also to add some software that would allow us to actually dig asteroids out of the data in basically real time. So basically we took some software that is very similar to that used by Pan-STARRS, and we basically retrofitted it to work with the WISE cadence. And we call that the moving object pipeline. It was run twice a week, and basically we delivered what we call tracklets, position time pairs for the asteroids, to the Minor Planet Center here. And MPC receives all of our tracklets and basically figures out which asteroid does it correspond to. So the idea was to do that fast enough that if we saw something that looked like it could be a near-Earth object, there would be enough time to quickly go get ground-based recovery of the object, because we only observe an object for typically about a day or a day and a half at a time. And that's not really enough to see where it's going to go. It's enough to say broadly, this might be a near-Earth object, but it doesn't allow us to really nail the orbit down or predict impacts or anything like that. So basically, the chase was on to do this year-long observing run, essentially, and get follow-up from places all around the world to try to nail down near-Earth object orbits. Okay, so here are some of the team members, and we're partnered with IPAC for our data processing, and we've got a slew of postdocs who've been very helpful. And we have also worked with a number of folks like Dave Tholen at IFA and Tommy Graf, who is a former student here. So why would we want to look at asteroids in the infrared? Well, there's a few reasons. The basic physics is pretty simple. The asteroid fluxes consist of a reflected light peak and emitted thermal peak as well. And the thing is that the reflected light flux is a much stronger function of albedo, the reflectivity of the object, compared to the emitted flux. And this has a couple of different consequences. First off, the infrared fluxes are basically insensitive to albedo. So a dark object is equally bright, more or less, at infrared wavelengths as a bright object. And that's important because we know that quite a lot of the near-Earth objects are very dark, and thus they're easily missed by the visible light surveys. So that's one thing. The other thing is, since we have this pretty good sensitivity to diameter rather than albedo, we can actually nail down diameters quite well. And this breaks the degeneracy between an object that's small but highly reflective and large but very dark. So if we have good measurements that span the rotational light curve, which we usually do, we can almost always get the diameters to within about plus or minus 10%. And that's compared to, that's a considerably better accuracy for the diameter than diameters that you derive from visible light alone, where you don't know if the object is bright or dark. And then, of course, one of the nice things about working in space, we're always looking at this low elongation region, which is kind of tangent to the Earth's orbit, if you think about it. So we're looking in a volume of space around the Earth that's difficult for the ground-based surveys to see. And, of course, we don't have any weather, so that makes it easy to understand the survey biases, or easier, which helps for extrapolating the population that we saw to what we think is really out there. Okay. So there's one other thing that's kind of an advantage, and that is the infrared sky is mostly blank. If you look here, the wavelengths are color-coded so that 3 and 4 microns are the blue and green wavelengths, so they look cyan, and 12 microns is red. And you can see there's really not a whole lot of red in the image. And the red things that you are seeing there are asteroids. This is what they look like to WISE. They're basically strings of dots. These are what we call tracklets, position time pairs. So the nice thing about this is that even though the telescope aperture is small, meaning that the spatial resolution is relatively poor compared to a larger visible telescope, the sky is relatively uncrowded. So there's a lot less chance of landing on a star or a galaxy, and that helps with confusion. That's why we can get away with using such a small telescope. Okay, so this is what a typical tracklet looks like. And basically, you can see we've got a series of exposures at 12 microns and 22 microns. And then we basically just look at a series of exposures before and after of the same patch of sky. And this helps us to figure out that there's not a star or galaxy there that we're confusing the source with. And then we also look for latent images, the exposures immediately prior to the ones we just collected. We require a minimum of 5 detections to figure that something is an asteroid. And what that allows us to do is basically be very reliable, meaning when we pull stuff out, we're pretty sure this is really an asteroid and not just a collection of cosmic rays, for example. So basically, like I said, our average observational arc, though, is only about a day and a half, which means we have to have ground-based follow-up relatively quickly or the objects get lost. And so Tim and his company at the MPC do a fabulous job of handling all the observations from the spacecraft and making sure that the word gets out to the ground-based follow-up community. Okay, so this is what we ended up with during the prime mission. This is sort of the solar system as viewed by the NEOWISE project. So you can see we're starting off here, and we're always looking at about 90 degrees from the Earth. So we're looking in a different direction than the ground-based surveys, which are typically surveying the regions closer to opposition. And each of the dots is an asteroid that we've observed. And the reds and the greens are the near-Earth object populations. The red ones are our discoveries. The greens are other people's. And then the comets here are the blue and yellow guys. And in total, we observed about 158,000 asteroids. So what this allows us to do that's the big difference from before, is now we can get sizes for these objects and reflectivities, albedos, which has some correspondence with their composition. So in the past, only a couple thousand objects have had any sort of either taxonomic classification or radar measurements to really nail down sizes. So basically, this gives us a whole new look at the physical properties of the small bodies in the inner part of the solar system. And you can see a few things here. I mean, here's our galactic plane passage. Even in the infrared, we are still confused by the galactic plane. The Jovian Trojans are right here. And you can see this right there is where we lost the 12 and 22 micron bands. That's where the gas ran out, so to speak. Actually, the frozen hydrogen, not gas. But this right here is the formal end of all of the cryogen, this red dashed line. And we were able to continue the survey for an additional 4 months just to fill out the inner edge of the solar system right here. And on February 1st, the mission was placed into hibernation, and that was the end. That was it. So what did we learn from all of that? Well, like I said, we have a sample now that we can debias because we can measure its sensitivity and the properties that it should have seen. So the basic idea is you take the observed sample as a function of its orbital elements and physical properties, such as albedo and diameter, and then you basically model out the survey sensitivity as a function of all of these parameters. So the way we do this is we look for objects that have very well-known orbits, and we see how many of them appeared in a frame and whether or not we saw them. In other words, we look for what things should have been there and did we see it as a function of magnitude. And then basically what we do is, the other method we do is we take a synthetic population and we basically play that through a survey simulator, and we tune the properties of the input population until it matches what we saw. And that allows us to tell that, okay, these are the properties of the underlying population. So the basic idea is we're testing a set of orbital elements that we think represents the near-Earth objects in particular. We assign a series of physical properties like size distributions and albedo distributions, and then we basically just keep tuning those. And we basically say, okay, let's calculate the position of each object in our synthetic population. Let's calculate a model thermal flux for it at the WISE wavelengths, and then see whether or not we should have found it based on what we know about the sensitivity of the instrument. We also have a complete list of all of the pointings in the whole survey, so we know exactly where we pointed and when. And so for each frame, we basically calculate what should have been in the frame and did we see it. And then we just keep tuning the parameters until we get an output of the survey simulation that matches what we saw. So what did we learn? So that's basically, I just said in words what's on the chart here, so we'll ignore that. A couple things came out. So the first thing is when we looked at reflectivity of asteroids as a function of size, there was something that was immediately kind of obvious, and that is that the distribution of albedos, the ratio of bright stuff versus dark stuff, which roughly corresponds to the objects that are primitive carbonaceous objects versus stony objects, or more processed objects, is roughly the same as a function of diameter over a fairly large range of diameters. So all the way from pretty large sizes, kilometer sizes, down to hundreds of meters, the ratio of bright to dark is roughly the same. And that's contrary to some previous studies which found that asteroids were supposed to get brighter as you got smaller. Well, we think that that was actually an artifact of selection bias. In other words, if you have a visible light survey, it's harder for you to see the small dark stuff. So you could mistakenly infer that it's not there. We think that it is there. It's just that if you select based on the thermal flux, which basically doesn't depend on the reflectivity, now you see the small dark stuff in its accurately represented proportions. So that was one output. And then we can try this thing where we basically say, okay, here is our 12 micron selected sample. So this is the sample in the previous plot, selected on the basis purely of its thermal emission, compared with a sample that was selected based on its optical fluxes. And sure enough, now as you get to smaller and smaller sizes, there does appear to be a clear trend of the asteroids getting brighter as they get smaller. But we think that this isn't real. We think this is probably selection effect. If you select based on the optical flux, of course, it's harder to see the small dark stuff. But if you select based on the thermal flux, well, you see the dark stuff just fine. So maybe there is a real effect down here at the very smallest of sizes, but at this point it's tangled up with the selection biases of the visible surveys. And so we really can't say for sure what's going on. But my bet is survey selection. Okay, so one of the things we were able to show is that by using our model populations, we found that, yea, verily, we pretty much are unbiased with respect to albedo, as you would expect. And because this is an all-sky survey, we're actually pretty sensitive to the higher inclination orbits, which are harder for the ground-based surveys to see. So when we back out the properties of the underlying population from our survey simulation, what we found is that there are actually somewhat fewer near-Earth asteroids out there, larger than about 100 meters, than prior estimates had suggested. And we figure that there are about 20,500, plus or minus around 3,000 near-Earth asteroids. Now, I'm not including comets at this point, just near-Earth asteroids, that are larger than 100 meters, and of those, about maybe 25% have been discovered. So the size-frequency distribution is a little shallower than previous predictions. Now, what that means and why that is, we don't know. But it does set some constraints on the formation of the near-Earth object population that need to be satisfied. When we look at the matches of our sample population to the predictions from the orbital element models, it's a pretty good match, with a couple of exceptions. More or less, the distributions in semi-major axis inclination and eccentricity look pretty close to what we would expect. But there were a couple things that stuck out, and I'll get to that in a sec. But basically, now we can also use our model of the albedo distribution combined with the known population of objects to get an estimate of how many have actually been discovered to date. In other words, what fraction of the population remains to be discovered. And there's some good news. At the 1 kilometer and larger size, remember we said we weren't sure if there was a class of large near-Earth asteroids that were being systematically missed. And it doesn't look like there is. From our predictions, we think that basically all of them have been found, about 90% or more of 1 kilometer and larger NEAs have been discovered already. So that's good news. The less good news is when you get down to about 100 meters, only about a quarter of them or so have been found. Now, overall, the population estimate that we come up with is, like I said, less than the prior. So that's also good news. For very small stuff, though, in the size range of Chelyabinsk, the NEOWISE sample is just really insufficient. We really can't say anything about objects that small. That's a different sample you'd have to work with. So, in short, I mean, basically, there are fewer NEAs, but it's still a lot of NEAs. It's still pretty crowded. So these orange objects represent the known objects at present. The red ones are the old model population. These blue ones and white ones are the NEOWISE sample. You can see we discovered a couple retrogrades going backwards here. Funny little things. And so this is what we thought. And this is our new estimate of the population. So fewer, but that's still a lot of asteroids. And these are just the ones larger than 100 meters. So there's still plenty to find and lots more work to do. And one of the other things we found is as we cut our sample down to just consider those that are actually formally classified as potentially hazardous, there were some other interesting things that came up. So a PHA could also mean perfectly harmless asteroid. It doesn't mean that the asteroid and the Earth will ever be at the same place at the same time. It just means that the orbits get close together, that's all. So it's a population of interest because perturbations can kind of pull things around on timescales of about 100 years. So we want to pay attention to these ones in particular. But in general, there's a zippo chance of impact, and it's not something you should lose any sleep over. But we do want to know how many there are. So we cut our sample down to just consider the PHAs. And of course, now the error bars are going up because we have many fewer objects in our sample. But we figured that there are about 4,700, plus or minus about 1,500 out there that are larger than 100 meters. And again, about a quarter of these have been discovered. The remaining 75% are still at large. But when we looked at the distribution of potentially hazardous asteroids that occupy the lowest inclination orbits, in other words, the orbits with inclinations most similar to Earth, we find that there are about twice as many as the model predicted. So that's good if you're looking for places to go that take very little energy. It's less good from a hazard standpoint, but we would like more data.
So just a random comment, right?
Yeah.
People didn't read the paper close enough. I got phone calls from people saying, how dare you publish a minimum estimate for the number of near-Earth objects? Like 2 PIs of surveys called me and said, oh, you lowered the hazard. I said, read the paper.
Read the paper. Yeah, it's a kind of a nuanced result. Fewer overall, but the average NEA poses absolutely no hazard. The ones you want to watch out for are these ones, and particularly the low inclination orbits. So we would like to get a little more data to see whether or not our result holds up over time, but that's what we came up with. Anyway, so the data have been used for a wide range of different things, not just the study of the near-Earth object population. We can apply these sorts of debiasing studies to all the different asteroid populations that we saw and to the comets. We can also look at things like the collisional histories of asteroids, in particular asteroid families, groups of asteroids that are thought to have formed from a single collision. And we can also do some tricks to basically look at the size distribution of dust that's emitted by comets. We can also look at some of the volatiles that they contain, the CO and CO2. And we can also find what I like to call our weirdos, things like Trojan asteroids that actually share the Earth's orbit, not Jupiter's. Turns out we actually have one. I'll tell you about that in a minute. And lots of fun stuff like that. So when we consider the distribution of asteroid compositions in taxonomy, this is from Francesca De Meo and Rick Binzel. This is kind of the classification of asteroids. They're near-infrared and visible spectra. And they span a wide range of types, basically from things, all the way from things that are extremely red objects to things that have flat or even very blue spectra, to things that show different spectral features in them that allow them to be classified based on composition a little bit. And when we considered the fraction of objects, I mean, one of the first things you want to do when you have a new data set is you basically take what you have and then you cross-reference it to whatever else is in the literature. So the first thing we did is we basically took all of our diameters and albedos and started plotting them versus objects that had classifications like this to figure out were there any correspondences. And this is what we found. So basically, as you look versus diameter, these are mostly for main belt asteroids now, and compare the albedos, what we find is that, sure enough, as you would expect, the stonier objects, the S-complex objects, tend to have very bright albedos, and the more primitive carbonaceous object classes tend to be dark. But as you get to small sizes, there's this curious uptick again. And I would submit that this is not because there are no small dark C-types here. It's because when you go to do spectroscopy to classify them, you have to see them in visible light. They have to be pretty bright. And sure enough, I'm sure they're there. A large fraction of the asteroid belt is dark. So you have to be careful. I guess the moral of the story is selection biases really matter. And before you infer that there's a change in material properties of asteroids at small sizes, you have to be pretty sure that you haven't just not observed part of the sample because you couldn't see them. So that's one of the things that came out from there. Francesca De Meo, and Francesca, I'm sorry I'm presenting your chart for you, but she's done some really interesting work to show, by combining Sloan Digital Sky Survey color data with WISE, to show that there's some interesting things that crop up when you look for different types of asteroids in places where they really shouldn't be. It turns out these very red objects, these D-type asteroids, are thought to be very primitive objects that should have been formed far out in the outer parts of the solar system. And sure enough, they pop up in some curious places in the inner part of the solar system where they're really not supposed to be from existing models of how the solar system formed. So when and how these objects got there is going to be an interesting story. And it suggests that perhaps the early solar system was a more chaotic place than perhaps it was initially thought to be, and not so orderly in the process of forming these small bodies. So that work is really getting underway. The other thing we found, like I mentioned, is just like Jupiter has Trojan asteroids that are gravitationally stuck to that planet, it turns out Earth has a temporarily captured Trojan all its own. It's known as 2010 TK7, and it's orbiting about the L4 Lagrange point right here. And you can see this is basically a plot showing its libration cycle, which is about every 400 years or so. And it seems to be captured there for roughly 7,000 years. And after that time, it'll eventually get jiggled away and go off onto its own and become a regular near-Earth object. But we were able to see it by virtue of the fact that we observed near 90 degrees. As you can see, looking at its orbit, it basically never crosses 90. It doesn't really come out past that. So you have to be looking here pretty continuously to see things like this. I'm a bird watcher, and one of the things I like to think about with bird watching is if you see one thing, it's probably common. There's probably more of it somewhere. So my guess is maybe there are more Earth Trojans out there, temporarily captured objects like this, but we just have to be looking in the right place to see them. So we hope we can set some limits on the population at some point. And it's a pretty large object. It's close to 400 meters across and reasonably dark. Okay, so some of the other work that's going on with my colleague Joe Masiero at JPL, he's been using the sizes and albedos measured by the WISE mission to recalculate the ages of asteroid collisional families, and basically trying to figure out, where are the family members, and can we use albedo and color information to identify new ones. And a number of people have been doing this work. There have been a number of great papers that have come out recently to combine Sloan data with WISE data to try to find the smallest members of asteroid collisional families and help refine their ages. So you can see here there's some pretty distinct groupings in semi-major axis versus inclination. And these family members all seem to have fairly constant albedos, so that suggests they really did come from a common origin at some point in the past. When you remove them, you can see that there's still some residuals left over, but this background gradient may be closer to the original gradient that was left over from the formation of the solar system. So that's a lot of stuff remaining to do there. And of course, with comets, we have a really large sample of comets now. It's close to 200 objects, including a couple dozen new discoveries. The thing that's useful about this is, if a comet is inactive and we can see its nucleus, of course we can get the sizes, which means we can calculate the size distribution. And in principle, if we can get all of these nucleus sizes figured out, we should be able to apply the debiasing formalism to understand the true distribution of orbital elements and sizes among the comets. Now, for active comets, of course, you can't get a nucleus size, but what you can do is figure out the sizes of the particles. You can figure out their abundances, and you can also even calculate, in some cases, the particle lifetimes. How long does it take for the particles to get flung off the comet? So there's a lot of great work that can be done there. And this is like what I like to call the family portrait of the comets WISE. We don't get to choose the name. That's the IAU rule. They're all called WISE, or NEOWISE. But they're a diverse and kind of motley bunch, and you can see they span the gamut from some very, very active objects to things that are really barely active at all. So there's a lot to be learned about how comets become active as they approach the sun, and hopefully these data will contribute to that. Okay, well, one of the nice things about doing a large survey like this is that it really provides the community with a resource for trying a lot of different experiments. And this has, for me, been one of the most exciting things is, obviously I have the projects I'm interested in, but it's been really satisfying to see all the great things that everybody else is coming up with. And the WISE main mission, the baseline, is now up to something like 1,100 refereed papers, and even just the NEOWISE data, just the single epoch exposures have been given rise to a couple hundred papers so far. And they really span all kinds of different subjects. So like I said, that's been fantastic. I'm really happy to see that. So as it turns out, I mentioned that the spacecraft was put into hibernation in February of 2011. And we did that because that was the end of the prime mission. We agreed with NASA that it was done. We still, however, could use the 3.4 and 4.6 micron channels, even though they had run out of gas. So what happened is basically in August of 2013, NASA asked us for a proposal to restart the spacecraft, just using the two remaining channels. And we turned it in, and basically what we needed to do was this. In the hibernation state, the spacecraft was kind of parked just pointing up, if you will, just sort of pointing just at the North Pole, just up. The thing is, at this point, we're viewing the Earth for half an orbit. So that warms it up. And basically, the telescope got to a couple hundred Kelvin in a very short order. So the question was, would it cool back down? And basically, all we did was we resumed zenith point. So we just basically stare at deep space at 3 Kelvin. And sure enough, after about 3.5 months, the telescope re-equilibrated, and it's now at about 74 Kelvin. And that's cold enough for our 2 short wavelength detectors to operate with very low noise. So sure enough, we got the first good images here. This is Astronomer Christmas and Hanukkah and New Year's and all that. It was a lot of fun. And it came right back. And 6 days later, we had discovered our first new near-Earth asteroid after we switched it back on. So it really worked beautifully. So the goal of the reactivation mission now is to basically continue surveying for near-Earth asteroids and comets. And the goal is not so much discovering large numbers of them, because this satellite was never designed to do this. And with its 2 remaining channels, it's never going to discover a lot of objects. But it does contribute a couple of unique things. It's possible to get sizes and albedos, which is very difficult to do if you have visible light alone. So that's good. It also lets us discover the large objects. We're particularly sensitive to large, very dark NEOs. And this is a segment of the population that's harder for the visible light surveys to see. And what we're hoping to do, of course, is with the extra survey data, we'd like to be able to set some constraints, even if they're rough, on some of the more exotic populations like the Earth Trojans and some of the co-orbitals. And that just takes a lot of imaging. And of course, we see a lot of really fun objects. Like this is one of the comets. I think this is Comet Pan-STARRS up here, zipping by. And so, of course, we can still get size distributions. The first thing we did was check whether or not the telescope had been affected by the hibernation. It hasn't. The image quality looks pretty much the same. The photometric 0 points are unchanged. Sensitivity is pretty much unaffected. So that was good. And there's our first NEO. discovered 6 days after we restarted. And basically, just to show the phase space that NEOWISE is really good at, is basically, again, here's that familiar diameter versus albedo plot. The black points are the new discoveries. And this particular plot's a bit out of date, but you get the idea. Big dark stuff. That's what we find. So that's the unique contribution of NEOWISE, and contributing lots and lots of albedos and diameters for these objects. So we're observing roughly about 0.7 NEOs per day, so we're trucking along. So after 3 years or so, we should have observed a couple thousand objects, if you include stacking, by the time the mission ends. So here's one of our fun finds. A little weird stuff like this comes up all the time. We discovered this asteroid, and it turned out it was going to make a very close approach about a month later after we discovered it. And sure enough, about 3 lunar distances. Well, this was close enough for such a large object that it was actually a beautiful target for radar. And the thing is, this would not have been observable otherwise by anybody else, because we found it at minus 72 declination, and it stayed there basically right up until the day that it made the close approach. So it would have been unobservable to folks on the ground. And sure enough, when we got the radar image, it was really kind of gratifying to see this, because the light curve of this thing was really quite large, very large amplitude light curve, suggesting that it was a very elongated body. And the effective spherical diameter computed from the thermal fit was around 330 meters. And this was the little world that was revealed to the radar. It looks like a bowling pin, kind of. So sure enough, elongated, and about 370 meters along the long axis. So the neat thing is, if you can take a radar shape model and combine it with infrared observations, you can get out a unique property. You can actually get the thermal inertia of the surface. There's really not a good way to get that except by doing this technique. Otherwise, you have to go to the asteroid. And what this tells you is whether or not the surface is covered with bare rock or fine sand. So it gives you an important clue as to the nature of what's on the surface. So in any case, like I said, NEOWISE was really never designed to do this kind of work. But we've learned an awful lot from it, and it's been an important prototype. So what we'd really like to do is design a new infrared telescope that actually is optimized for finding near-Earth objects. And we very creatively call it the Near-Earth Object Camera, NEOCAM. Like I said, not a particularly spectacular acronym, but you get the idea. And the idea is basically to solve a couple of logistical problems with WISE to optimize this mission for really going after the near-Earth object population, and not just observing a couple thousand, but observing almost all of them larger than a certain size. Basically, observing most of the really big stuff that's out there. So the idea is basically to make something that looks kind of like Spitzer, with a couple of important differences. No cryostat. The idea is to go to the Earth-Sun L1 Lagrange point, where we can basically get cold enough that we can passively cool to about 35 to 40 Kelvin, and just put on a whole boatload of modern detectors, megapixel detectors, and from there we can just stay there. Passively cooled, we can last for quite a while, and just survey the whole region near to the Earth. One of the other key changes is to be able to look inward from 90 degrees to about 45 degrees solar elongation, that's the region of space around the Earth's orbit where the most hazardous objects spend a lot of their time. And the idea is to basically just sit out there and repeat the survey over and over and over again and look for most of the near-Earth asteroids. So we were actually awarded technology development funding in last discovery rounds, in the last discovery round. And that allowed us to mature our infrared detectors. So we've been able to make some new infrared detectors that actually work at 10 microns at 35 Kelvin. These are Mercads, which ordinarily cut off at 5 microns, and we've been able to extend that out to about 10 now. So hopefully we'll be reproposing this in the next discovery call whenever the AO is out, which is hopefully very soon, and we'll see what happens. So thanks very much for listening, and especially thank you to the Minor Planet Center for hosting all of our observations. We really appreciate it. Thank you.
Great talk. There must be many questions.
You just stepped through this plot briefly, I think a little bit after you quoted Francesca's results. Something about a medalist remaining. Could you say a little bit more about that?
Yeah, let's see here.
Sorry, I can't be more specific than
So one of the things,
that's a very nice, colorful
I
plot.
should not speak for Francesca here, but basically, one of the things, if I can speak for Francesca, is basically she's found that there's a lot more mixing of different taxonomic types than previous studies have suggested. Basically, things are in places where they really shouldn't be or where they're not expected. So now, as far as the metallicity goes, it's really hard to infer a metal composition for an object. It takes a lot of different parameters to be able to constrain that. But there has been some work recently where people have tried to look for things that have anomalously high beaming parameter. It's basically a kind of catch-all parameter in the thermal models. If that number is very high, it is possible that an object could have high thermal conductivity. Could also mean some other things, but it's kind of a place to look. And that work's been done by Al Harris and Una Gerbe.
I think you had a plot just a little bit after this one that on the right-hand side of the screen was showing some subtraction of the metallicity gradient and what remained after that.
Oh, yeah, the families. This one, right here?
Yeah, I think
Yeah, so basically, if you remove the collisional families, this is what's left over.
yeah.
And that shows the gradient from high albedo to low albedo. So the idea is to try to pull out the families so you really can get a good look at what that gradient looks like. That was one of the reasons for finding the family members. So.
Question?
Yes. Is it possible to look for the Chelyabinsk impactor in the NEOWISE archive or something?
So we actually tried that, and it turns out we just didn't cross over that region. It would have been vanishingly faint. This is such a tiny object. Now, the smallest thing we've dug out of our data so far is roughly 8 meters, but it had to be about 3 lunar distances away for us to see it. It's just very faint, very small.
Could you back up to the taxonomy quantity where you're showing, here. So you make the point that you don't think that what you're seeing is selection. I mean, there is a selection effect here, sorry.
Yeah.
But what is the uptick of the orange points there?
So,
So if you're just following that along, why does it turn out?
right, we actually think that this is scattering. So as you get to smaller sizes, your error bars are getting larger. And what's happening is it's like if you clip off half of a Gaussian,
Okay.
you're actually not seeing the lower
Yeah, okay,
points. You just
okay.
can't see them. They're there, or they should be there.
Yeah, okay.
But yeah, what's happening is the error bars are actually getting larger on the ensemble. As they get smaller and fainter.
Erwin.
Early on, you mentioned that the main asteroids have been there for billions of years, but the so-called near-Earth asteroids, NEOs, have only been there a couple of orders of magnitude less time, quarter millions of years, and they're young. Now, I'm not sure what you meant by young. You don't mean they were created only this.
Yeah,
you mean they were
dynamically.
put into these orbits only that long.
That's right. Yeah, they're dynamically young. That's right. And I kind of glossed over that whole process, but exactly how the near-Earth object population originates from the main belt asteroids is a whole other story, and there's a whole lot of work that's being done to basically try to confirm ever-improved models of exactly how the NEOs got from the different source regions within the main belt and the comets. And that's one of the things we'd like to be able to work on. We think that there are certain preferred regions and resonances that basically give rise to the NEOs. You would suspect that the size and albedo distributions of those source regions should look similar if you convolve them all together to the NEOs. So that's one of the things we'd like to look at some point. Hopefully somebody will do that.
When you when you mentioned that you've cut down the estimate of the number of asteroids by factors of, say, 3 from something between 100,000 to 20,000, what was the error made in the original estimate, the larger estimate? Is there anything to be learned from that?
Yeah, so the errors in the previous estimate are fairly large, I think. It's 36,000 about 100,000. Now, as more survey data are collected, those numbers are being refined. But at the time that this paper was published, that was sort of the leading number right there. It was sort of 50,000 to 100,000, roughly. And they don't put as stringent an error bar on that estimate. So one of the things we've been able to do is, because we're sampling the size distribution directly, we don't have to convert from H, that gives us an ability to really try to hone in on what the real error bar actually is. So we try to do our best with that. Tim? You have a comment?
Yeah, I think the issue with the original model was they were using a bad albedo, mean albedo calculation, right?
Yeah.
And that was probably why they were coming up with more objects.
That's possibly it, yeah.
Okay.
Yeah.
So NeoCam, will that start to fill in the smaller objects below 100 meters?
Yeah, it's actually going to find quite a large number of them. I mean, so, you know, there are a lot more objects at the small sizes than there are at the large sizes, of course. So even if you find a smaller fraction of them, you're still finding a large number in an absolute sense.
I'm surprised because the curve goes way up just at 100 meters, and it's like terribly unknown how many there are even at 50.
Yeah, that's one of the things we'd like to settle. Exactly how many are there?
So one of the limitations I saw, just because it was a one-year mission, was that while you saw a lot of near-Earth asteroids, they kind of all tracked around you.
Yep, that's right.
And so you really had a subsample with a tremendous observational bias, because it was just everything that happened to be going along with you.
Right.
So how were you able to go from that, which looked to sort of identified everything that was right around you, to say we've discovered 95% of all the large objects?
Right, so one of the things you do is you basically look at a lot of different child populations. And, you know, the thing about this is it's true that you're observing a spatially local clump, but they represent a broad diversity of orbital elements. And that's one of the things. The other thing is, are there classes of objects that we missed? There might be a few, but I mean, we surveyed the whole sky, so we weren't missing the high inclination population, for example. We were sensitive to regions of orbital element phase space that are harder to get on the ground, like the high inclination objects, for example. We think it's a pretty representative sample.
I mean, just when you look at that, you see all the new NEOs near the Earth are clumped,
right?
Because you can only look.
You worry about, you know, biases in mean anomaly, for example, but we haven't observed anything that suggests that there's something unique about this particular group that we happen to see. This is why we would like to do a larger project, though, because there are certain things you just can't answer with this sample size beyond a certain point. You can't cut the sample down anymore and infer much about it.
Well, along the same line, if you pull up the plot of the co-orbital.
Yeah. Yes, our sample of one.
Yeah. So, where in the orbit was that discovered? Right at the tip of that?
Yeah, right there.
Okay. Right there. Okay.
Yeah, because they don't get out to 90 degrees very often.
Nope.
Yeah.
This was really lucky that we just happened to catch this object. It has about a 300 or 400 year libration cycle.
You really can only see the things that have the longest libration speed.
That's right. But that's kind of one of the interesting things about these is I think a lot of these things actually do librate. They don't sit right at the Lagrange point. So a lot of them are going to poke out eventually. But they just won't because they can't get too close to the Earth and still be a Trojan. So you really can only see them at low elongation.
If you go back to the census that shows the different size classes and what percent group time.
Yeah, the completeness.
It's like one more, yeah. So it looks like below 500 meters or so, we really start losing, like, we start losing a large fraction of the population. How hazardous are the objects at like 300 meters or 100 meters where we don't really have a good census?
They're bad.
How bad?
Severe regional damage, basically. They're bad. You would not want one of those to impact us without a lot of warning. I mean, one of the things we try to do is, as my colleague Don Yeomans likes to say, that the three best things you can do to mitigate asteroid impacts are find them early, and find them early. Basically, if you design a survey that looks for objects when they're decades away from impact, then you can actually do something about it. So that's sort of what we're trying to do here with this.
So if finding them early is so great, that implies that you could maybe even predict sort of how they would come in and where they would land. Is that really true, or do things get pretty chaotic right at the end, depending, very sensitively on angle in the atmosphere?
Right. So one of the things is, I mean, when you first find an object, you know very little about it. In one day, Tim is the world's expert on this right here. I mean, he can speak to it way better than I can. But basically, with one day of observations, like what we get, you can broadly say it's an NEO, it's not an NEO. To say more than that, you obviously have to keep watching it on the appropriate cadence so that you keep extending the arc out. And you really want to have, about a month of observations of it. If something ever popped up, though, that's of particular interest, the whole community dogpiles onto it. The Apophis object is a really good example of that, where that looked like it had some potential impacts. And of course, the community immediately started to observe it. And that almost always refines the chances of impact drastically downward. In other words, because it's a matter of the size of the uncertainty ellipse, right? You have a large uncertainty ellipse first, and as you get more observations, that gets narrower and narrower, and so of course it's almost certain to miss the Earth. But basically, you know, this is this whole network here. At this point, what we have is I would say, a very good network of warning. In other words, if you input observations into the network that there's an asteroid, it immediately goes to the Minor Planet Center, it goes to JPL, and they have a really fast response system for figuring out if something is an actionable hazard. But what's missing are just more observations. So that's kind of how we answer the question.
Actually, following up on that, if you get the NEOCAM and you find an object that's in this arc of, you know, less than 90 degrees elongation to the sun, how can you ever get an orbit?
Well, that's the thing. The survey has to do its own follow-up.
Okay.
The cadence has to be designed so that it doesn't rely on ground-based follow-up. So what you have to do is you basically are kind of building a sort of a geometrical progression in time to extend the arc out from one day, you know, from a few hours to a day, to a few days, to a month. And at that point, once you have about roughly a month's worth of observations, you have enough to go on that you can pick it up again when it makes the next apparition. So, I mean, for most of the objects, that's more than enough, right? Because you know, oh, not hazardous, throw that one back. You know, interesting for science purposes, but not for hazard calculation. In other words, we might want to know something about its orbit and its evolution, or its characteristics. But you're really only looking for the ones that are actually an impact hazard, and those are the ones that you're going to spend extra effort trying to observe.
So is it better to be in L1, or would it be better to be at a, you know, I don't know, a 9-month orbit around the sun?
So we've actually looked at that pretty extensively, and it turns out it's not better.
Okay.
Just because if you're at L1, you can survey so much of the volume around the Earth that it does just as well. And then the problem is the minute you go into a non-nearby orbit, you have a huge data rate problem, and you just get killed. Because it's no good having 30 megapixels worth of pixels if you can't get the data back. That's a real problem.
For the smallest, darkest bodies that you guys can detect where the sensitivity bias is extreme and visible, what sort of E magnitudes or R magnitudes does that correspond to?
For NEOWISE, the faintest things that we typically find, the absolute faintest, are going to be of 23 when we discover them. And it does actually make some of the follow-up pretty challenging, because sometimes we find stuff and it's, you know, the typical follow-up observer network is sort of 1 meter class telescopes. So every now and again, we've actually begged and borrowed a little bit of time from DECIAM, which has been great, to follow up some of the really faint stuff, the really dark objects.
So is this something that we wear LSST or, you know, will really
Yeah, I mean,
fill in the gap?
Absolutely. I mean, having a very deep, sensitive ground-based survey would be very complementary for a couple reasons. It would help to extend the arcs, find more objects, but also that's how we get albedos.
Yeah.
You want albedos because that tells you something about whether it's carbonaceous or stony in a very general sort of way. So yeah, the survey has to do its own follow-up, but we would really love to have physical observations to get the albedos. And one thing I forgot to point out, all the data from the Prime mission are public. They're available at URSA through the Infrared Science Archive, so if you just go there, you can get access to all of it. And our next data release from the restart is coming up in March, next year.
Last question? Yeah.
Sorry, I feel like doing another like amateur hour asteroid question. So how chaotic?
You should see me with quasars.
How chaotic is this? Like, are there? I guess like, is there a large sample of asteroids where they're not hazardous now, but we will want to check on them in 50 years, and maybe suddenly it'll be like.
Yeah, that's the definition of PHA, actually. I think that gets back to the definition of what a potentially hazardous asteroid is. It's basically something that gets within 0.05 AU of the Earth's orbit, the object's orbit, not necessarily the object at that point in time. But the reason that they chose that particular number is if you look at perturbations from the other planets, that's enough on about a 100-year time scale to say that you can't unequivocally rule out an impact. So these are the ones you really want to pay attention to. And again, it's all a question of orbital knowledge. How well do you know the orbit?
And 100 years is kind of the time scale for.
Yeah, roughly.
All right. Thank you very much.